Wow, I'm popular. Or GPT is popular, probably the second. So hello, welcome to my presentation. So first things first, last minute changes. I talked to the WolfSSL booth in the business hall yesterday, and they felt excluded because I'm only talking about their competition. So I spent an evening, and we'll be doing live WolfSSL as well. So that's that. And let's go with it. Let's go on with it. So who am I? I'm founder and CEO of Meyer Labs. This is a software house and consulting firm. So we're doing reverse engineering, embedded IoT, security, secure coding, high-performance computing. So basically anything that requires deep hardware knowledge that would be interesting to us. I'm also a founder of CloudVA, and CloudVA provides access to side channel equipment. So you get a VM with side channel software and hardware included. And we can do side channels as a service. We can do side channel regression tests, for example. And we also have GPT integrations. So agenda. Intro, we're here. First, why do it? Why do this? Why do side channels at all? Why combine this with LLMs? Then how to do it, and I will concentrate on hardware requirements, software requirements. I will briefly mention strong sides because everyone talks about it, so that's not really interesting. If you want to know why GPT is great, you can read about it elsewhere. I will concentrate on the problems and the workarounds that we had, and you may need also to employ if you want to work with code specifically and in context of security with GPT. There will be a live demo, of course, and the presentation I hope will be useful for you if you're doing GPT integration, if you're processing code with GPT, or if you're using GPT in context of security. So let's start. GPT intro. I assume everyone knows what GPT is at this point, but just a quick intro. This is the most popular, I think, LLM at the moment, large language model. The important parts that may not be as well known is that March release included plugins, which lets GPT access physical interfaces, web services across, across the internet. So this gave GPT a kind of power across the world. So you can basically do anything that is online with GPT. GPT can call a web service for you. And in August, there's an analysis mode also, and GPT can now run natively Python code. At the moment, we personally are not using it because these are either or. You can get GPT with plugins or with analysis, but not with both at the same time. Analysis is very promising for code and for binary object manipulation, but at the moment, it's not useful to us specifically. So if you look at the bottom right there, this is the plugin screen, and these are a couple of plugins that I'm personally using, and one of this is ours. So we developed a plugin, and basically what we do is we give GPT access to the infrastructure that we provide, that CloudVA provides. So intro to side channels. So what are side channels? Who knows what side channels are? OK, a couple of people. Good. So basically, computers are physical devices. Shocking, I know. So physical devices have physical side effects. So computation takes time, computation takes energy, computers emit radio emissions, of course. All of these things can be measured. And if you measure precisely enough in time and space, you can figure out what the computer is doing through these measurements. So the attacks that we will perform today are based on power measurements. Correlation, we will be doing correlation power attacks specifically. So this is an example of a power trace. This is advanced encryption standard. This is how advanced encryption standard looks from our point of view. And There are tiny differences between if you run advanced encryption standards on different inputs with the same key. There will be small differences in power and consumption, and we will use these differences to recover the encryption key. Of course, this is a noisy measurement. So this is a probabilistic model, mathematical model that you need to calculate, and you need to have enough samples to kill the noise, basically. But it's a practical attack if you have physical access to the device. There are also active side channel attacks. So basically, the first three are passive. The second three can be active also. So you can inject faults into the chip. You can shoot lasers at it. You can shoot electromagnetic impulses at it, or you can provide not enough voltage to the chip, which makes it behave weirdly, or you can overclock it past the point where it's stable, and sometimes this leads to interesting results. This is also something we can do, and also something that is available on cloud, but we're not giving access to ChatGPT access to that, because these are not safe attacks, like they can damage hardware, so that's currently offline, but the first three are live. So my point is that side channel attacks are easier than most people think. Yes, there is a high barrier of entry. Like I said, there is a mathematical model, quite complicated, that needs to be calculated. You need to have physical access to the device, and you have special equipment, in particular oscilloscopes, to do the power measurements. But once you get past that, the attacks are remarkably portable. So everyone we've been using, as security professionals, we've been telling people for decades never to roll their own crypto. So pretty much everyone uses the same library in IoT and embedded, and pretty much everyone uses the same hardware. So ESP, whatever, or STM32, whatever, right? These are the most common. And the point is that once you crack one of them, the attacks translate to many chips and many implementations. So for traditional attacks, every time a new firmware comes out, you have to go in and find a new zero-day, find a new buffer overflow, because pointers change, layout of memory changes, and so on. For us, we just rerun the same CI pipeline. We literally have a side channel pipeline on GitHub. So here's a demo that's advanced encryption standard on STM32F3. And now we broke the key. So the attack is 12 seconds, this one. This is not the best attack we have. And the fact that it's 12 seconds is interesting, but not the most interesting part about the attack. The most interesting part is we can perform the exact same attack. I don't mean a variation of, I mean the exact same code across, I think, 6 STM32F whatevers that we've tested across all 3 major AES implementations out there. So like 95% of the market. The exact same code. If you're using hardware AES, that's more like 2 minutes, but same argument. So why do side channels? Basically, the sad state of IoT hardware security is vendors use the cheapest microcontrollers they can. Of course, they do. So these are non-secure elements. So an example of a secure element would be, I don't know, an NXP semiconductors chip that you have in your ATM card, for example. These are protected against side channel attacks at the hardware level. But these ESP microcontrollers and most popular microcontrollers aren't. They have low clocks, so sub 100 megahertz or sub 200, let's call it. They have 0 countermeasures against side channel attacks, and they are essentially deployed in hostile environments. You have IoT devices, embedded devices that you deploy around your home, not in your home, but around it. And they have access to your data, they have access to your networks. And essentially, attackers have physical access to these devices. Cost of attack these days is basically a laptop and a $100 picoscope oscilloscope, or 200, I think, something dollar chip whisperer. So basically a clever teenager threat level with his lunch money. And I gave this argument last year, and the most common response is, yes, the cost of hardware went down significantly, but you still need experience and you like a team, hardware security team to do that. And my point today is, yeah, we got GPT to do that. So that's the idea. So why do GPT? Why include GPT in this? First, GPT on its own is already aware of some timing, some side channel attacks, so it can do time invariant code on its own if you ask it. And so, of course, hit and miss with GPT as usual, but question is, what else can it do? Our hope is to get GPT to generate low-cost countermeasures. And basically, we want to do this with automatic training. That's the big idea for next year. We have infrastructure to perform attacks, and we want GPT to generate countermeasure, test the countermeasures on our infrastructure, and learn from all that. So basically, the biggest bottleneck in AI is generating the training data, the samples to get the model trained on, and we can do this automatically, or semi-automatically, anyway. So that's the idea, and on the right you have an example of a time invariant simple password check that GPT generates on its own. So how to do that? How did we achieve this? So first, hardware. We use PCI Express pass-through USB controllers, and basically after that, anything that's USB can be connected to our cloud. Oscilloscopes, chip shouters, chip whisperers, protocol analyzers, debuggers, whatever you want to have, you can have on a VM with a very good speed. And the examples that we include here, the pictures, is a high-end oscilloscope. On the left there's a chip whisperer in the bottom right, and above it is chip shouter. So these oscilloscopes are used for the passive attacks, for the power measurements, and the chip shouter. This is injecting electromagnetic pulses into the chip and basically flips bits inside it while the encryption is running. So we can change state like that. Software. For software, this is pretty much a standard virtualization stack. So Linux, QEMU, KVM, libvirt, and on top of that we have a RESTful API. The long story short about this is 2020 we had a hardware security project going on. We lost access to our own lab because lockdowns. So just to work remotely, to be able to work remotely, we had to make this online. And after that, basically, we had a web interface across the whole thing. So we figured, OK, why not do GitHub integrations? Why not do let's do GPT integrations? So that's how this started. So we do this by implementing GPT plugin. And the essential part of the GPT plugin is the open API specification of your endpoints that you will be providing to the GPT. So this basically tells GPT when to use your API, in what context to use it, what to call, how to call it, how to interpret the results, and also other prompt instructions that you would like it to do. So don't do this particular thing, or after you're done, do this particular thing. Also, important bit is examples. I will get through that later as well. So these are top-down. These are our endpoints that we provide to the GPT. So it can list, create, VM, start, stop. That's not the interesting part. The interesting parts are these three that are highlighted. So it can build a device under test code. It generates device under test code itself. It can build it with this endpoint. And the second endpoint is gather power traces. So it can gather power traces on its own. And at the end, there's the correlation power analysis. It can also do that. And if you describe these endpoints to GPT, here's an example of the CPI endpoint. It can with some prompt engineering, it can properly use this. So here's an example. These parameters here that only describes the parameters that are present in the URL. The rest of the parameters are in schema. I'm not showing the whole thing because this is quite detailed. So this is actually 187 lines of code, if I believe, the CPI endpoint on its own. So here are a couple of examples of details that you need to provide GPT to do this correctly. So for example, early days, it would frequently fail on link because it would generate its own main function, but we provide the main function, so we tell it not to do that. We also tell it that all the symbols should be static to also limit link issues. And we also tell it what other libraries we provide so that it can use them instead of trying to implement them. And here's an example that actually fails. We tell it that this function computes whatever, but actually GPT tries to use this function frequently, as an array, not like a function, but like an array, like a lookup table. So this is already an example of a hallucination, really, where GPT ignores one of the instructions. So the next big part is that examples matter more than descriptions. And here's an example. After we did these 5, it stopped using the HW as an array. It uses now it correctly like a function. And examples are interesting because they are token denser than descriptions. They provide more context, so they provide in the same place, they provide an example of parameters and types of parameters, for example. And they also can help GPT understand what the defaults are if you don't provide arguments for the function. So here, for example, the first example tells GPT that 255, so integer, is a valid input to this function. So strong sides of GPT. Boilerplate. It knows APIs, so Chip Whisperer API, OpenSSL API, WolfSSL API. It knows better these APIs than I do. It can write examples, use cases faster than I can. Even though I worked with these libraries for years, it literally types faster than I do. So it's useful already as a productivity tool. It's just faster. I can concentrate on hard problems, and it can type for me. But that's not like most powerful use. The powerful use that we think is going to be great next year also is translations. So we can generate code from an English natural language description. It can translate between languages, so Python to C, C to Python, for example, but also it can translate a scientific formula to code. And we want to do that as well. So basically, we want to be able to say, hey, GPT, here's a paper. Read the paper, extract a leak model from it, and implement it on our infrastructure. And it almost works. I will cover that as well later if we have time. And it's pretty good at self-correcting if you provide feedback. So here you can see that one of these examples, it can fix build issues, link issues. If you provide it with STD error of the build system, it will most of the time it will fix the problems itself. Python imports, and this one time, it literally told me to go fix my cables. So it told me we have a problem with a loose cable in the server room, and it was right. So even things like this, it can sometimes guess. And now the problems. So the biggest problems, the first 4 as the biggest problems that we still have trouble with. The next 3 are problems that were present in, say, April but they are less of an issue, or not of an issue right now. There was a big release in August of GPT-4, and this fixed many of the problems for us. So context size, of course, context size is limited to 4,000 tokens. This is not a lot, especially for code. Hallucinations, it will sometimes basically lie to you. And blob handling, so binary large objects, it has no interface at the moment to handle large amounts of data. And it's not fast, so it gets timeouts frequently. So here's an example of a context size problem for code processing specifically. So at the right, you have an example of a constant, 64-bit constant, and this is 17 tokens, but worst case, it can get up to 20 tokens per 64-bit element. So if you have an array that is 200 elements, a lookup table in your code, basically your analysis is dead at this point, because you already exceeded the context size. So example of this, April 2023, it was unable to produce a complete AES S-box. Because of this, it was unable to produce a 200-element random array. It would like hang in about halfway through. It would just freeze and abort, timeout. As of November, as of like yesterday, these problems are fixed, but it's still unable to process large pieces of code. There are workarounds for this. So we do token size optimizations on code that we process. And here's an example. You can basically hide the constants. For example, you can define the constants in a header, hide the header from GPT. And this particular one, this is a 3-to-1 reduction in token size for this lookup table. So process only what you need, what you absolutely need. Move what you can, abstract what you can. Provide clear naming also, because if you provide clear naming convention, then you can hide type definitions, and the model can infer the type from the name, which is less tokens than the header. And defining the constants away, this is the example that we have here. ID token size optimization. So XKCD had a decent idea a couple of years back that if you're working with humans, it's good to have your passwords and names compatible with humans. And the same argument applies today to AIs. If you're working with AIs, design the systems to be easily understood by AIs and to be easily remembered by AIs. So universal UID, entropy is 128 bits, but it's 18 tokens. That's a lot. The XKCD examples you can see there, but what we propose, and we're not yet using it, but what we propose is TOC4, which is 4 random tokens. The token, there are 100,000 tokens, I think, so this is more than 16 bits, but we assume you won't be able to use all of them because white spaces, special characters, and so on. So I assume 16 bits per element and 4 elements. That gives you 64 bits of entropy with just 4 tokens. And this is also a 3-4-to-1 reduction from UUID to TOC4 in IDs, in the identification and names that you can use. Hallucinations. That's a big one, and it's not entirely solved for us today, so we still hit hallucinations. Basically, it will lie to you. It will make up plausible but non-existent APIs, libraries. It will ignore instructions. So, for example, it will, in our case, we have a PA tools module that we implemented ourselves, and it's repeatedly trying to import utils component from it, which doesn't exist, and we never told it that it exists or anything else like this. So it basically assumes that this module exists, and it fails to import it. But if you actually return this error, it will fix it itself. So basically, here we said the module does not exist, so it wasn't able to use the HW function from the module, and it implemented the function itself, and it injects the function in the code on its own. So if you fail early, if you return meaningful messages to it, if you provide concrete descriptions, concrete types, it can fix its own problems. Or if not, really, you can also give in and implement what it's missing. This is also an approach that we considered at some point, and we do this in one case at least. So if it's repeatedly trying to use a function in a module that is yours, it's probably easier to just implement it than fight it. So binary objects, it basically doesn't have any interface to process that. So if you ask it for a random array, for example, it will fail. Here, there was an error. Basically, anything larger than a couple hundred elements is probably too large to process with GPT today. So the fix for that is you have to store data on your own end, even relatively small amounts, like a couple hundred elements. You only pass names. You would use ID optimization, which we currently don't, but we discovered this after the fact. So next major release, we'll certainly fix that. And if you need the model to manipulate the data, the insights of the data, you need to provide create, read, update, or delete API to this data. Of course, delete is problematic because hallucinations, and also because the chat is persistent and there is no clear destructor that you can call. Like, user can shut down the website and you never know whether it's going to be used, the context, whether it's going to be used again or not. So that's one. Timeouts also are a problem still. There are 3 examples of timeouts. GPT is not fast, and the worst part is it's inconsistent. So at the peak hour, it can be several times slower than say at night. And these plugin calls are just HTTP requests, so subject to request response timeouts. GPT has no sleep or wait mechanism, so it will happily retry a failed request, but you can't say, please wait 5 seconds or 15, and it will not. So it will not respect retry after header or anything else like that. So to fix timeouts, we optimize response timeouts. So our provisioning takes less than a second. VMs respond to ping in 3. They are fully ready to serve GPT endpoints in less than 10, and it's still not enough sometimes. So next step is building asynchronous APIs. So return an ID immediately and basically perform work in the background. And if it asks for the data, if you're not ready, just return 503 in reasonable time, and it will retry again. So live demo. We will try to do this live. We'll see how it goes. So you can see here's my plugin enabled, and we will just ask it. We'll just ask it that. So it lists the VMs that are available on Cloud VA. It found one that is already running, because I'm prepared. So it's using it. Now it's writing the device under test code. So basically, this is an AES encrypt use case. Now it's going to build it. And in a moment, it should perform power measurements. Yeah, this is a bit slow. Sometimes this is about average, I would say. It's not the worst. So here's the important part. This is the leak model, the critical part of the correlation power attack. It just implements the critical mathematical model. It just passes it. And OK, I need to scroll up a little bit. So it guessed, rank 0 means that it guessed the correct key, the correct byte, or the correct value of the first byte of the key. So basically, it just performed the analysis correctly and guessed the correct key in the first try. So let's do WolfSSL as well. So you can see it's including the WolfSSL headers. Basically, again, a use case of AES encryption with WolfSSL. Now it's going to build it. And do the power traces. And again, it correctly recovered the key here. So we're currently only attacking 1 byte of the key, but it can do the entire key at once if you let it. I am actually surprised that this worked. First time it almost never does. So I will show you a thing that fails, and I wanted to actually show this. So I want to show you how it's fixing the build issues that it's encountering on its own. So here, there was a small race condition. We did not mount correctly one of the endpoints. So it's going to retry. It's basically doing the same request again. And it failed to build the example because it wrote mbedTLS AES encrypt function, which already exists. We return the complete STD error of the build system. And once it sees this error, it will properly fix the problem. So it will rename this function to a custom AES encrypt, and that works afterwards. So this is an example of self-correction. OK, let's go through the conclusions. We have, what, 6 minutes? OK. So let's go through the conclusions. Can it do side channels? Yes. If you give it the infrastructure to do that through a plugin, yes, it can do that. Can it solve hard problems? No, it's not like really intelligent. It won't invent new attacks, let's call it. But it's useful still. It does enough of the boilerplate, and it does iteration fast enough that you can use it productively. Even for us, I can tell it, here's 15 leak models that I want you to test, and tell me which one is the best, and it will do that. I can tell it bisect to find how many traces it takes to break the key, and it will do that as well. So it's useful for cases like this even now. So hopefully, you'll learn a little bit about how to build a GPT plugin from my talk. Hopefully, you learned a little bit on how to work with code. And hopefully, you learned that side channels are easy, or at least easy enough for GPT to do, and easy also easier than you thought, I hope. 4 minutes. OK. Let's So here are a couple. You can do this live, by the way. The plugin is live. The Cloud VA is also live. So you can use these prompts. Of course, you need an account with us. But other than that, you can use these prompts to have fun with ChatGPT. And you can, changing leak model to whatever just works. Bisecting works. Extracting leak model from papers almost works. So you can upload or paste a paper into GPT and ask it to extract the interesting parts out of it. And the biggest bottleneck that we've seen so far is actually loading the paper itself. If you type the formula correctly, you're on your own, it will generate correct, maybe not optimal, but correct code. But the problem is with loading the paper itself, like parsing the PDF. OK, 3 minutes. I guess I can take some questions. Then. Yep. Can you, yeah.
Test. Would you see ChatGPT-5 being able to do differently from ChatGPT-4?
So 5, I would expect it to fix hallucinations primarily. That would be the biggest problem for us. Also the large data handling. So it's already on the way. The analysis mode can already do that, but there's no integration with plugins. I would expect this to be integrated at some point. This would help massively because this is a language model, not a mathematical math model, so it cannot really, do math. So now that it can run Python code with the analysis mode, it can actually do math, and that's a massive improvement. So I would expect for code that would be the biggest 2 improvements.
Thanks, buddy.
Thank you for your presentation. I do struggle to see the added value of having an LLM here because essentially you use it to call an API, so it's not using any new side channel techniques. So what if like the time you used to basically script using the LLM was used in just making a wrapper around your API?
It's not really scripting. We perform the analysis, the code for the analysis, the leak model. It's generating its own leak model. So it's guessing the leak model as well as the device under test code. All we are doing really is basically doing the heavy lifting of interfacing with hardware.
Okay, so it guesses the leak model out of the results of the calls that it makes to your API?
Yes. So for example, if you do simple password test, you can, for simple password, you can do comparison with XOR or subtraction or regular compare. It's a bit hit and miss, but it will guess leak model as well. So it will use subtraction leak model for subtraction comparison.
Okay. Thank you.
And the biggest idea after that, this is not a production system at the moment, but the biggest gain we hope to have from this is the auto learning. So generating countermeasures, testing them, and learning from this process.
Okay, thanks.
All right, thank you. Here are my links.